Hello. Okay, good morning, guys. We'll get started. It's about 10 o'clock, maybe a few ticks before, but I'd like to finish this session early. I have another online meeting at 11:30, so there won't be any office hours today, and we'll try and finish this up before 11. I think we can do that. Okay, so let's go ahead and start with worksheet 10. Okay, let me just admit a few more here. Okay. All right, guys. Little rush hour into the waiting room there. Okay. Forgive me if I have to stall a little bit to admit people. So chapter 10 is about correlation and regression. I think I've mentioned regression before, where we try and relate two variables, x and y. And the relation that we're looking for is simply a linear relation, okay? Not anything more complicated than establishing a linear relationship, which, remember from your algebra class, is graphically symbolized by the equation, let's say y equal to a plus bx, where a is the y-intercept and b is the slope of the line. So all we're going to do in this chapter is take two samples, x and y, typically from different populations, okay? And in this first example, we're going to try and establish if there is a linear correlation or a linear relationship between x, which is the rate of chocolate consumption. By the way, this example is talked about in your textbook at the beginning of chapter 10, right? So we want to relate x with a variable y, where, as I mentioned, x is the rate of chocolate consumption and y is the rate of Nobel laureates. Okay, just a few weeks ago, you read in the news about various Nobel laureates in various disciplines. And so it seems a little amusing that we would relate chocolate consumption and Nobel laureates. It seems like there wouldn't be any sort of a relationship, but in fact, this example goes ahead, and we'll see how we solve these problems, and you'll see how we relate the two variables. And sometimes x is called the independent variable, y the dependent variable, okay? Or x might be called the predictor variable, and y might be called the response variable. So these are all terms that you'll read about in chapter 10, okay? So in this first problem, we've listed the data in a table here, all right? And the table lists the chocolate consumption in the X column and the rate of Nobel laureates in the Y column. okay? And in the text, the author talks about these different rates for different countries. Okay? So we don't know which country this relates to, but apparently it's real data. Okay? So the first thing we want to do in order to understand if there is a linear relationship is to simply graph x versus y in a scatter plot. And we can do that quite easily in StatCrunch, and I'll show you how to do that. Okay. And then we'll inspect the scatter plot, and we'll ask if there are any outliers in the data, any points that don't look like they follow the clustering of the other points, all right? And this is a tricky subject because we never want to delete data from our data set, do we? From our sample, because we've taken the trouble to collect it. And on the surface, we don't have any reason to believe that it's not a real data point that pertains to the data at hand. Nevertheless, we have to be cognizant of any outliers that arise in the data in order to not skew the results in an unjustifiable manner, okay? And then we'll inspect for outliers, and we'll inspect, more importantly, to see if there is a pattern that shows increasing values of the Nobel laureate rate with increasing values of the chocolate consumption rate, okay? So let's go ahead and graph the data here. And in StatCrunch, you use your graph superfunction, go down to your scatter plot, and then fill in the action window with the data that you've listed. Here, what works very nicely in your document that you'll download from your assignments page, you can simply highlight all of these columns here and copy and paste them right into StatCrunch, okay? So use that tool, simply highlight. Really all we need are these two columns labeled X and Y here. And you will copy and paste those right into StatCrunch, and then use your graph function with scatterplot. And here you get the scatter plot of Y, the rate of Nobel laureates, versus X, the rate of chocolate consumption here. Now, when you stare at this scatter plot, you see that, in fact, increasing rates of Nobel laureates does relate, or seems to show, a relationship. As the rate of chocolate consumption grows, so does the rate of Nobel laureates. So what we're studying in this chapter is, how can we quantify this pattern that we see in this plot? And furthermore, if there are outliers, can we identify those, either leave it in or take it out? And you can see up here, there's a value here, and the value is in our data table here, happens to be 6.4 on the x-axis, and about 31.9 on the y-axis here. And let's see if we can identify that point up here on the table. So I'm looking for the value, the x value here, 6.4, and here it is down here in here, okay? But we don't have any information that leads us to believe that it's not part of the data set. We'll go ahead and leave it in. If we had some evidence that it is an outlier, maybe a typo, maybe some other anomaly, we could leave it out. If we did leave it out, you can see that there's a strong linear correlation between x and y here, okay? Here's another point that looks marginal, okay? So inspecting our plot gives us a good idea of some of the basic characteristics of this relationship, including the fact that it might be linear. Well, in statistics, we do have a way of quantifying the supposed linear relationship between two random variables, x and y, two random samples, okay? And we're going to study that a little bit here in number 3 here. Okay, so let's look for a more objective measure. And the statistical measure that we're going to use here is called the linear correlation coefficient, denoted by R for the sample. Okay, we have these two samples, x and y, so we can calculate R. And we'll use that number to quantify the strength of the linear relationship. What do I mean by strength? Well, could we fit a straight line through these data points in the scatter plot? Okay? And would that give us a way to predict a value of y given a value of x? Okay? So we might want to use this graph to build a straight line passing through the scatter plot, and that would allow us to create a prediction equation, an equation that we'll call the regression line. Okay? So how does the value y respond to a value of x, or how does the dependent variable y depend on x? These are sorts of questions that are used in applied statistics to associate a random sample x with another random sample y from presumably two different populations. Okay? So the formula is given to you on page 480 in your text. So please refer to formula 10-1 in your textbook. And it's wise to familiarize yourself with that formula. However, StatCrunch will automatically calculate that for us. Okay? There are some algebraic properties of R that we should be aware of. First of all, in absolute value, it's less than or equal to 1. Yes, it may be negative. Here we envision a straight line passing through the scatter plot that has positive slope, right? As x increases, so does y. But in fact, we could have another situation where as x increases, y decreases, which would give us a negative slope in the straight line that fits the data. And one can show using algebra that R in absolute value is less than or equal to 1. Or another way to say that is that the absolute statistic R varies between -1 and 1. Okay? And algebraically, when the correlation coefficient R is 0, that would imply that there is no correlation between X and Y. Okay? So we wouldn't want to predict a value of Y given a value of X because there's no linear correlation between them. So you see this value R varies from -1 to +1 on the real line. And when it's close to 0, then that indicates there's no correlation between X and Y. So in order to fit a straight line, we need to first calculate what R is, see where it falls in that interval from -1 to 1. And furthermore, we have a statistical test that will allow us to provide a p-value for the null hypothesis that the population correlation coefficient, which is denoted by rho, is equal to 0. Okay? We'll come to that in number 4. So let's first calculate the correlation coefficient as given to you in the formula in your textbook. Okay? All right, so we'll go ahead and calculate that value and figure out where it lies in this interval. We know it's going to be positive. Okay. All right. And let's go ahead and do that. Let's go ahead and calculate the linear correlation coefficient R as given in the formula 10-1 and as calculated by StatCrunch. Okay. And if you use your summary stats superfunction and go down the list to correlation, okay, and when you choose this function correlation, you will fill in the usual action window with the 2 columns of data in your spreadsheet, X and Y. Okay. And then you'll get a calculation that R is equal to about 0.8. So it's way up there, very close to 1. So this indicates there is a positive linear correlation between X and Y. Okay, all right. Okay, now let's associate a probability value that sort of nails down our previous conclusion that there is a positive linear correlation between X and Y. And if we use this test, okay, we can calculate its p-value from StatCrunch. And again, if that's low, if the probability value is low, we will reject the null hypothesis that there's no linear correlation. And we can safely conclude that at some significance level, alpha, whichever we choose up here, that there is evidence in the sample for a linear correlation. Okay. And so we can again do that in summary stats. Okay. And when you do this calculation in summary stats using correlation as your function, the StatCrunch will show you the p-value. Okay. In parentheses, you'll see the p-value next to the value of R, which we calculated in the previous problem to be about 0.801. Okay. So when you run this calculation through StatCrunch, do this test, you get a very small p-value. Okay. When the p-value is low, the null is a no-go in favor of the alternative. And so we can now fit a straight line. Okay, let's look back at our logic. Here we have chocolate consumption and the rate of Nobel laureates. On the surface, we wouldn't think that there's any relationship between them, but you can see with this analysis that we've just done, we can fit a straight line through that data and possibly use that straight line to predict, given the value of the independent variable x, a value of the dependent variable y. That is, we can use x to predict y. Okay? So let's go down to the last problem here. Can we fit a regression line? And the regression line is fitted using a procedure called least squares. And all least squares does is it uses a maximization procedure, which is easily done in the calculus. We're not assuming calculus in this course, but what least squares does is it takes the difference of the value of the blue dot here and subtracts it and squares it from the value on the predicted line. And then it minimizes the sum of those squared error differences. Those are called the residuals. So how do you find the line which creates the minimum sum of residuals? And that's what we're doing here. So that special line given to us by the calculus is this red line that you see here. And how do you do that in StatCrunch? Well, you'll go to, again, the stat super function. This time you'll choose regression. And then there are some choices there, and we're using this first choice, simple linear regression. And it will then fit the straight line for us. Okay. Okay, and here we've gone through all the steps. Now we have our fitted line. And let's predict a value of the response y given a predictor value x of 5.5. Okay, let's check our data here back at the top. All right, and notice 5.5 does not occur in the x column here. So can we associate a value y to the value x equal to 5.5? Well, what we're going to do is use our predictor line, okay, to calculate a response y for the value x equal to 5.5. 5.5 is right here, 4, 5, 6. So it's halfway, it's about 3/4 of the way from 4 to 6. So we're asking for what is the value on the red line for the value x equal to 5.5. Well, StatCrunch gives us the equation of the line. Okay, so it gives us the least squares regression line y equal to -3.36667. We could round that, but I just wanted to leave it that way to show you what your StatCrunch output will look like. Okay, and then here's the slope of the line. It's about 2.5. And the value for x is substituted here. Remember, this is the line a plus bx. So x is 5.5. Go to your calculator now and calculate the value. 2.4931337 times 5.5 plus a negative 3.366667, and your calculator will spit out the number about 10.35. Okay? So this is our predicted rate of Nobel laureates given a rate of chocolate consumption to be 5.5. Okay. All right. Now, another question up here was, should you use this predictor line to predict values outside the range of X? What about if we wanted to calculate the rate of Nobel laureates given an independent value X equal to 20 or 30? Notice that our range really is within the interval from 0 to 12. Okay, the range of our data X is only shown to you here in the scatter plot to be from about 0 to 12. So if we go outside that range, we need to be careful, because remember what least squares did, it only used the data values here, X and Y. So typically we would be very reluctant to predict a value of Y given a value of X, which is not in this range of X here. Okay? So that's how least squares linear regression works. Now, I've left out a lot of details here of how you do this in StatCrunch. I've given you the clues on how to do it, and follow these steps carefully as you go through your StatCrunch calculation, and you'll be able to reproduce all of the results here that I've shown you in the solutions. Okay? All right, guys. Do you have any questions? Any questions about what we've done here? Okay. So copy and paste your X and Y columns right into StatCrunch. And we've got some time here. Let me go ahead and show you some of this in StatCrunch. Okay. So can you all see the StatCrunch spreadsheet here? Everybody good?
Yes.
Good. Okay. All right. So as I indicated from the document, all I did was highlight and then did a Command A or Command C, excuse me, Command A to highlight the data, or just highlight it, and then do your Command C to copy it. And now when you're in StatCrunch, paste it. No need to type in each of these columns of data one by one. Just copy and paste right from your word processor document, and then paste your 23 X and Y values right into StatCrunch. Okay, now we'll go to graph here and pick out the scatter plot function. And as usual, we get a dialog or an action window. So we'll select our independent variable X for the Y variable, for the X variable, our dependent variable Y, okay, which is our response variable. We'll skip all of these options, okay? All right. Okay. And again, I can label the axes, and I do want to see labels for these axes. So you'll have a label here, X, the rate of chocolate consumption, Y, the rate of Nobel laureate, okay? And I'll put a grid on it. And I won't take the time to type in the titles, but I want the titles. Okay, I want you to title, label your two axes, and then we'll compute. Okay, and notice that this is the graph that we showed you in the solution set. Okay, all right. If we go to summary stats, as I showed you in the solution set, we can take summary stats under the superfunction stat, and then over in this list, we'll choose the correlation function. And remember, that formula is given to you in chapter 10. It's the first mathematical formula in the textbook in chapter 10. Okay? We'll get an action window, choose our two candidates for the correlation, all right? We'll display the two-sided p-value. Remember, two-sided because our hypothesis test was rho equal to 0 versus the alternative rho not equal to 0. Okay. And there we get our correlation of about 0.8. And we get our two-sided p-value, which is less than tenths, hundredths, 10,000ths. It's less than 1/100,000th, right? It's very, very small. That would reject the null hypothesis, indicate that there is some linear correlation between the two. And now we can go to the line fitting. We'll fit the least squares line. If we get a high p-value here, we would not reject the null hypothesis. That is, that there's no correlation. That would lead us to believe that there's no correlation. We would reject rho equal, we would not reject rho equal to 0. But in this case, we get a low p-value, all right? So we can't accept rho equal to 0, and we have to conclude that there's some linear correlation. May not be strong. And in this example, it's marginal because it looks like there might be some outliers away from that line, right? Okay, but the R value is pretty high. The highest it can go is 1. That would be perfect linear correlation. Okay, so it's pretty high with a very low p-value for that test of rho equals 0. Okay? All right, and now we can go ahead and fit the least squares line. Choose your stat regression, your stat superfunction, go down to regression. Choose your simple linear. Select your two variables, x and y. Okay. And, excuse me. We'll skip over the hypothesis test based on the line. Okay. All right. Okay. And the significance level here is set to be 95% significance. Okay. All right. And I won't label the line. Let's use our grids again. And here we get some information. We get the equation of the line, which I showed you in the solution set. We see the correlation coefficient and so on. All right. And then in the companion output for fitting the line, we go here to the graph, and here you see the fitted line. Okay. All right. And all of these results I showed you in the solution set. Any questions about worksheet 10? Okay. Any questions about worksheet 10? Is this all clear? Some of you have started your chapter 10 MyLab Statistics homework, and you're already familiar with some of these methods. Okay, others have not started your chapter 10 homework. Okay, and please use StatCrunch to help you solve those problems. Okay, all right. Any questions about worksheet 10? Are we all good there? Okay.
Professor,
Yeah.
do we need a best fit line for the scatter plot or no?
No, you won't do the least squares line until you get to number 5. Okay?
Okay, thank you.
I know that you're trying to kill 2 birds with 1 stone. You're thinking, well, if I just go to this part, I've got the scatter plot. So what if I still have the line? I still have the scatter plot. But you know, use your scatter plot function there, and show that result in your solutions. Okay.
Okay.
This one is a little bit duplicative, isn't it? It's showing you the scatter plot again, but in order to show the fitted line, it wants to show you the scatter plot as well, so that you can see. And I wanted to give you another exercise, and let's take our outlier here. Well, I'm calling it an outlier. Maybe I'm being a little bit unfair, because when we leave it in, we still get a very high linear correlation coefficient of about 0.8. Okay, but what I thought about asking you to do was remove that value from your data set down here in data point 20. Okay, take it out. Now you have 22 values, and redo the fitted line with that outlier taken out, and see if you get an even higher linear correlation, which you will, and an even tighter fit, although you still have a couple of points out here close to 12, which will have great influence, because remember, we're minimizing the sum of the squared residuals, and it's very sensitive to these large residual values here. Okay, so it probably wouldn't make a lot of difference even if you deleted. And then you're probably wondering, well, why don't I delete these 2 points out here too? Well, now we're getting into some gray area of deleting the sample set when it's really telling us the true story. So that's why we're very careful about not treating these outliers as in a too cavalier manner. Okay, guys, if there aren't any questions, we'll end the meeting. I won't have office hours today. I have a commitment online for another meeting, so we'll skip the office hour today and get these in by Friday midnight. Tomorrow midnight is the deadline and Canvas for this worksheet. Okay, and then over the weekend, I'll assign the next worksheet. And do you like the Tuesday schedule rather than the Thursday schedule? Any thoughts on that? Should we go with the Thursday schedule till the end of the semester?
For Tuesday schedule, actually.
Somebody likes Tuesday. Sadie? Okay. Any other? Let's see.
Tuesday.
Tuesday. Okay. All right. Can I be the person to call the tie? Looking at the chats, it looks like we're almost tied there. Okay. I have some other commitments this weekend. I'm not sure how soon I can post the next worksheet over goodness of fit test contingency tables. But if I get that up and running, we'll schedule the next meeting for Tuesday. If I don't, let me slip it to Thursday, okay? Okay, guys. If there aren't any
Professor,
further questions, yes, go ahead.
would you mind if we stayed behind after class? I just have a couple questions to ask you. They're pretty brief.
Sure. Just
Okay.
for a few minutes, you say?
Yeah, it's
Yeah.
it's brief.
Okay, we can do that. All right then, so I'll end the meeting. I won't sign it off yet, so go ahead, Vivica, what's up?
Oh, I was just gonna, oh, I didn't really, okay. I'll just email you, it's okay.
Okay, yeah, unfortunately I can't end the meeting, and then because I need to record this part. But if you'd like to send me an email or send me a text message on the telephone,
Okay,
I'll try and respond to you as soon as I can.
okay, are you gonna upload this onto?
Yes, as soon as it finishes recording, I'll process it on YouTube and then I'll share that with you on Canvas.
Okay, thank you.
Okay, all right. Okay, guys. Bye now.